Okay, so here's example 2 for the chain rule. And we've got 4 different equations here that we want to differentiate, but they're all composite functions. So just some different examples that are going to help us get some practice to decompose the functions into outside and inside functions, and then differentiate using the chain rule. So let's look first at a. Y equals the cosine of 2x. Now let's practice a little bit in both notations. So I'll alternate between Leibniz form and function notation. But either way, we still need to look at it the same. We need to be looking for something that we know how to differentiate. And really, there's not a lot of options here, but definitely 2x. 2x is something that is really easy for us to differentiate. So this right here is a good candidate for being u. So let's just go ahead. That looks like divided by u. I'm going to undo that. So let's call u 2x. And then once we've made that substitution, y simply becomes y equals cosine of u. And if we remember, I'll just write it again, maybe not every time, but for now, dy dx in Leibniz form is, remember, dy du times du dx. So we just need to take the derivative of both of these. So the derivative of u with respect to x, du dx, that's a little bit hard to see. Try that again. Du dx is simply 2. And then dy dx here, the derivative of cosine, we've just recently learned is negative sine of u. And so when we apply the chain rule now, it's just the product of dy. Oops, I've written this wrong. I wrote dy dx. I really want dy du. dy du there. So dy du is equal to negative sine u times 2. So our dy dx, and this has a u, we really want our derivative of y with respect to x to be in terms of x, and we can do that as soon as we substitute back in for u. Remember, we defined u to be 2x, so I'm just going to say that dy dx, our derivative, is going to be negative sine, replacing my u again with 2x, of 2x times 2. So in other words, dy dx is negative 2 sine of 2x. And that's our derivative using the chain rule. That's the first one. Let's go ahead and move on. Let's look at b, the second equation, which they tell us is y equals the square root of 3x squared plus 5x. And again here, it's fairly obvious that what we're going to choose to be u, probably going to be this polynomial inside the radical. So we're going to call that our u. So u is going to be now 3x squared plus 5x. I said I'd alternate in notation, so maybe I'll do that. I'll rewrite my function y. This is going to be the same thing. We can think of this. We can think of y as f of g of x as two functions composed together. And that's going to be the square root of 3x squared plus 5x. So we've said that our u, is going to be the same as our inside function, which is g of x, which we've said is 3x squared plus 5x. And so now, if we define f as a function of u, we're just going to get replacing this, right? F is the square root of this, but it's going to be the square root of u. And using our rule in function notation form, we know that the derivative of composite function here, f of g of x, is equal to f dash of g of x times g dash of x. So what we want to find, we definitely need to find the derivative of f. Well, here we can see that if we have the square root of u, if you don't have the derivative of square root of x memorized, you probably should. If you don't memorize it, you could always rewrite it as u to the 1/2 and then apply the power rule. But we know it's going to be 1/2 square root u. That's our f dash x. That's our derivative. Now, if we substitute in g of x there, it's going to be really 1/2, not u. We're going to replace u now with our 3x squared plus 5x expression. So this part right here, becomes 1/2 times the square root of 3x squared plus 5x. And then we're going to multiply that by this part here, which we see, we haven't taken that derivative yet, have we? So I'll do that just down here. We know that the derivative, g dash x, it's just a polynomial function, so it's going to be 6x and then plus 5. So we're going to multiply by 6x plus 5. And then we can rewrite this. We can multiply into the top, and we get a fraction, 6x plus 5, all divided by 2 times the square root of 3x squared plus 5x. And it's not a particularly beautiful result, and you can see that it would have been very hard to calculate this derivative without the chain rule. But we were able to do it, and there it is. So that's great.